Hello friends, my name is Vivek Sharma. Today we can cover this interesting problem that's called maximum level sum of a binary tree. So we have been given the root of a binary tree and the level of its root is 1. So it starts with 1 but not 0. So that is the important point here. The level of its children is 2 and so on. So that's how it will keep increasing. So for example number 1, root 1 will have the at the level 1. Second label will have the label as a 2 and so on. What we need to do, we need to return the smallest label x such that sum of all the values of nodes at that particular label x is maximum, right? So that's what we need to do. Now let's check here in this first example with the help of whiteboard. So we check here the first label, right? So this is the label number 1. So let's say this is label number 1. And what is our sum at label number 1? So sum is also 1. Okay, this is label number 2, right? What is the sum at label number 2? Sum is 7 plus 0 and that equals 7. All right, label number 3. So this is label number 3, and what is sum at label number 3? Sum is 7 plus, and then this is minus 8. So this equals minus 1. So what is the maximum sum out of these three labels, right? So maximum sum is 7 because sum is 7 is the maximum, then minus 1 and 1, right? So we need to return 2 at this in this particular case, right? So because we need to return the minimum label, right? Of course here minimum maybe might be confusing, but if we see this problem itself, we will always start from the root node and then we will go down, right? And once we will just keep checking the sum at each level, then we will keep comparing as well. We will have another additional variable that's called max sum or something, and then we will keep a track of the maximum sum. Once we will once we are done with the traversal of this whole binary tree, at the end we will return, okay, this is my maximum sum and this is the corresponding level, and then we just need to return the corresponding level. We just keep a track of the maximum sum to keep a track of the maximum sum and the corresponding level. So just go ahead and return the label, that's it. So that is what we need to do. Hope this problem is clear. And another important point here is from the constraints here that we can have the negative as well, right? So number of nodes can be until 10 to the power 4, minimum is 1, and they can be minus 10 to the power 5 and plus 10 to the power 5, right? So they can be minimum numbers as well. All right, so now how we are going to solve this problem? So in order to solve this problem, we will start from the root, we will go down and we will do the label. So if you recall, like can use the label order traversal. In other words, it is like the pattern of the breadth first search strategy. So what does that mean? Breadth first search strategy says to us that we will start with one node, we traverse all the connected neighbors to that node, then we just go again, we just traverse again the next neighbors, and then we just keep doing the same thing. So let's go ahead and try to walk through what does that mean. So in order to use the breadth first search strategy, we use the data structure called queue. So we are going to use queue here, and we will start from the root. So we will go ahead and insert 1 here in the queue, right? Now we will poll 1 from the queue, and then we will check, okay, if left and right is not null. Yes, so left and right is not null. And also when we do this operation, when we do these operations with the queue using breadth first search strategy, we need to keep a track of the label as well, right? So let's say we are having here the variable that's called label, and we are at level 1 and we polled this, right? And then now we are at the level number 2 and we will check, okay, one, what is the left and right? They are not null, right? So one's left, so 1 is the root, this root left and right, they are not null. So we will go ahead and insert 7 and 0 to the queue, right? And then we will increment this label as a 2, right? Now we will poll 7 and we will check, okay, what is left and right? So left and right is 7 and minus 8. So we will go ahead and insert 7 and minus 8 to the queue, right? And now we are at the level number we are still not at the level number 3, right? Because we are still at the level number 2, and then we are inserting its children. So we just inserted its children, and then we will be checking the next element, that is 0 at this level. So remember, we are still at the same level because we did not we just traversed through only 7. We only polled 7, but we did not polled 0. So we will just go ahead and poll 0, right? And we will check, yeah, whether it's having left and right children or not, right? So in this particular case, 0 does not have any left and right children. It means we are not going to insert anything further in the queue, right? And now we will just increment our level as a 3. We will jump to the next level, that is 7. We will pull 7 from the queue, and then we will just check, okay, there is no left and right in the for 7. We are not going to insert anything. Same thing, we will poll -8. We are not going to insert anything for -8 as well, because there is no left and right children for -8 as well. All right, very good. So far what we did, we just used the breadth first search, or in other words, we just did the label order traversal for this binary tree, right? So we will just use the same template. In this one we can just add the maximum sum logic, but let's go ahead and code this approach first of all. Okay, so let's see if so maximum level of root, right? So root, so number of the nodes cannot be null, right? So basically there must be at least one node. So I am here skipping the base case, right? Because we will always get at least one value, one node. So let's say I am having the data structure called queue, and then we will just go ahead and insert root to the queue, and then we will check, okay, if queue is not empty. This is pretty much kind of the breadth first search template, right? We will just go ahead and take queue dot size. Why we are taking queue dot size? So that we can iterate all the elements at that particular level, right? So at the level 1 we will iterate this one node, at the level number 2 we will iterate 2 elements, right? So similarly, whatever the queue size will be there, that number of the times we need to iterate that particular level of that queue. So that's why we are taking the size. So size is nothing but here is the number of elements in that queue, right? And each level, whatever the number of elements will be there, that will be the size of queue. All right, so what we will do here, integer I equals to 0, I is less than size, I plus plus 3 node equals to queue dot poll. Here we will be checking, okay, if node dot left is not equal to null, then we will do queue dot offer node dot left. Similarly, we will check, okay, if node dot right is not equal to null, then we will do queue dot offer node dot right. All right, now as we process this I equals to 0, I is less than size, this is for one particular level, right? So each level we are just processing all these nodes at that level. Then we are going to the next level, we are processing all the nodes at that particular level. Then we are going to the next level and we are processing all the nodes at that particular level. That's how we are processing, right? So that's what we are doing. Now as I mentioned, this is for one level. Now after this we need to increment our level, right? So why we are incrementing level here? Because in label we have already been given 1 to our question. So if we will read again this problem, then it says the level of the its root is 1. So 1 is already given. Now we process this level number 1 here. We want to increment this level number 2, and then we will just go ahead and process the next level elements here in the for loop. Then we will increment the level number 3. That's what we were doing at the whiteboard. So now go ahead and return level, right? So this is pretty much breadth first search template. I did not do anything. Whatever we were just exploring here, I just copy pasted, I just converted this sort into the code. All right, now we need to do the maximum sum here. So in order to do that, in every label we can have int sum equals to 0, and whenever we are polling from queue, we can just simply get this value and then keep accumulating in the sum for every level, right? And then after every level, what we can do, we can just check, okay, and we can take maximum sum as well, right? So let's say maximum sum, that is, let's say integer dot min value. So why I am taking min value? Because remember, it can have negative values as well, as per in the example 2, right? So if it will have the maximum minimum value, it will, if it can have the negative values as well, I want the maximum negative values, right? So if I take it 0 here, then this algorithm is not going to work for the negative test cases, right? The test cases that contains the negative number. So that's why I need to take the minimum here, minimum value, and I will check, okay, if maximum sum is less than sum, then it means I need to do maximum sum is sum, and then this label equals to what? So here label I'm taking here label as a 1, and then let's take any other another additional label. Let's say it's -1, right? Default value is -1. If we did not find any label, then we will return -1. So let's say this minimum label would be label itself, right? And then we are done. So we are not doing anything special here. We are just using the breadth first search strategy, and then we just integrated this maximum sum logic inside that, along with this breadth first search, right? So breadth first search strategy is there. We are just taking some we are taking for every label. So every label we will just keep accumulating. So if we go to the whiteboard and if we check here, at the level number 1 we will have the sum 1. At the level number 2 we will just keep accumulating 7 plus 0. At level number 3 we will just keep accumulating 7 minus 8, and that is -1. So that's what exactly we are doing here, right? In this for loop. So for every level we just keep accumulating this sum. After exiting or after completing that particular level, we are checking, okay, if this maximum sum 7, is it greater than the previous sum or not, right? So initially, let's say some minus min value is there, right? So initially maximum sum will be 1. Then for the next level, we accumulated the sum as 7. Then we will check, okay, is it greater than 1? Yes. So we will just mark this as a maximum sum. Then we will check, okay, 7 is still -1 is greater than 7 or not? No, -1 is less than. So our maximum sum will still be 7, and the level will still be 2 here in this case, right? Because this is 1, this is 2, and this is 3 level. So we will just store this 2 as a level, and we will just accumulate, we will just store the 7 as a maximum sum. So in the end we will just go ahead and return this label, minimum label, and that will be 2. So that's what exactly we are doing here. Let's check the time complexity. Here will be the order of n, and the space complexity will also be the order of n. Why? Because in the worst case we will keep traversing each and every node, right? And in fact, in this particular problem there is no other choice. We cannot skip any node, right? We have to traverse each and every node because we want to find the maximum sum of any level, right? Any level. So we need to just go ahead and traverse each and every node. So there is no option here. So definitely the time complexity will be the n, that is n is the number of nodes, and the space complexity will also be the here the space complexity will be the number of nodes, number of maximum nodes at any particular level, right? So for example, the queue will be storing the number of nodes at every level, and then we are just polling, and then basically we are just storing again for that particular level. So whatever the maximum number of the nodes at one level will be there, that will be the time space complexity. So in the worst case, let's say if it is totally flattened tree or something, then we are just saying, okay, it will be the linear complexity, right? So in fact, if I have to define this, then this will be the maximum number of nodes at level, at any level, right? So whatever the maximum number of the nodes will be there at any level, that will be the space complexity, because that's how many numbers queue will hold. I think this makes sense. Thanks a lot. Have a good one. Bye.